Okay, this video is to help you understand relative humidity and the page that I'm actually looking at is actually page number 80 in your textbook. Okay, this video is expected to take about hopefully less than 10 or 15 minutes. Okay, so let's begin. What do you need to know about relative humidity? Now, first of all, you need to be able to define relative humidity. That means to say, tell me what is it all about. Okay, next, after you've able to explain what relative humidity is about, you need to be able to describe and explain how temperature is related to relative humidity. That means I'm talking about how temperature and relative humidity are related to one another. How does A affect B? How does A affect B? How does temperature affect relative humidity? Now, once you've understood this relationship between temperature and relative humidity, we are going to apply this relationship to help us understand condensation and rainfall. In other words, we are going to see how it actually plays out in reality in the formation of a rain. So let's go to the first one. What exactly is relative humidity? Go to your notes now. Okay, you should see this page of hand-printed notes. Now, what exactly is relative humidity? Now, mathematically speaking or formulaically speaking, basically it's the actual amount of water vapor air can hold, and the units is grams per cm cube. Basically, how much water there is in every volume, the actual amount versus the maximum amount it can hold. I repeat, actual amount of water vapor air can hold and the maximum of water vapor air can hold. Now, you times this by 100%, you get a ratio. Now, those who are not good with maths, you don't understand, never mind. Let's look at a diagram that will help us better understand this. Now, let's take this volume of air for example. Okay, this volume of air, this box represents air, okay, and basically there is water vapor in the air. Now let's say this is 1 cm by 1 cm by 1 cm. Okay, that's the volume, 1 cm by 1 cm by 1 cm. And basically in it, I have 4 grams of air. 4 grams of water vapor. Okay, in a volume of 1 cm cube times 1 cm times 1 cm gives you 1 cm cube. In this volume of air, I have 4 grams of water. So basically, this is the current amount of water vapor in the air, 4 grams in every cm cube. However, you can see quite clearly there's still a lot of space here that can be filled up with water vapor. So, how do we know how much more water vapor there can be? We use this relative humidity to tell us. So, say hypothetically, if we know that the maximum amount this cm cube can hold is, let's say, let's give a hypothetical 200 grams of water vapor in this cm cube. The maximum is 200 grams. The maximum it can hold is 200 grams. Now, that means if I have 4 grams currently and my maximum is 200, how many percent of my air is actually currently filled with water? I use 4 divided by 200 times 100%. I will get, this is 1 over 2. 5%, right? Correct? No, this is 2%. Currently in this box, only 2% of the volume is filled with water vapor. Currently, 2% of the volume is filled with water vapor. In other words, there is another 98% of the air that I can fill water vapor in. Okay, so this is relative humidity. Relative humidity does not refer to the stickiness, right, or the dampness of the air, but rather it's a measure of how many percent of the air currently holds water vapor. In this case, it's 2%. So the definition is the actual amount of water vapor air currently holds expressed as a percentage of the maximum amount of water vapor air can hold. Okay, this is what relative humidity is about. So we cover the first objective, define what relative humidity is. Now, if you are concerned about the actual wording, okay, this is the actual wording. This is the actual phrasing of the definition. Okay, now the second part of this video is really to help you understand, how does temperature actually affect relative humidity? How does temperature affect relative humidity? Now let's go to these notes now. Now, what you see here in this graph is a graph with two vertical axes. Okay, on one axis you have the relative humidity. Okay, and the relative humidity is indicated by the blue line. Okay, in your notes it's black. On the right axis we have temperature, and the red line represents temperature. Now, what is this graph over a period of time? This is over a period of 24 hours. 24 hours. So, reasonably, if you look at the red line, in 24 hours, temperature reaches a low, the lowest, probably in the middle of the night, and it starts to increase as the sun rises, and it reaches a peak in say afternoon, and it starts to reduce as the sun sets. So this is a series of temperature data for 24 hours. Temperature going down and going up and going down in 24 hours. Now, scientific research has told us that basically when temperature goes up this way, goes down and goes up this way, this is how relative humidity looks like in the air. This is how relative humidity looks like in the air. You can realize immediately when the blue line goes up, temperature goes down. When temperature goes up, blue line goes down. When temperature goes up, blue line goes down. When temperature goes down, blue line goes up. They are always in opposite direction. They are always in opposite direction. Okay? So we are going to find out how come when temperature drops, my RH will increase. Why when temperature drops, my RH will increase? Okay? Now, let's look at this diagram here. Let's look at what happened when temperature drops. So we're looking at this part of the graph. When temperature drops, RH should increase, RH should increase. Now, let's say this is the block of air we are talking about. When temperature drops, basically there is contraction. The whole thing becomes smaller in volume. However, the amount of air, the amount of water vapor did not change. Only the volume changed when temperature decreased. Contraction causes volume to reduce. Okay, from 20 degrees to 10 degrees, volume reduce. Now, the current is 4 grams. The current amount of water vapor it holds is 4 grams. And the maximum it can hold previously is 200 grams. This is a hypothetical figure. Now, what happens when air contracts? The same amount is still present. However, because the box has become smaller due to contraction, now you have lesser ability to hold water vapor. As a result, you see the numerator remains the same, the denominator changes. Let's look at how it affects the relative humidity. If we do a calculation, 4 divided by 200, this should give you 2%. However, in this case, when temperature has dropped, air has contracted, the maximum amount you can hold has decreased from 200 to 100. 4 divided by 100, you actually get 4%. So what this essentially means is that with the same amount of water vapor, when air contracts, it loses the ability to hold more air. It cannot hold as much air as previously. Therefore, because my maximum has decreased, the current amount seems to take up a larger percentage of the air now. That means in the past, my air is only 2% filled with water vapor. currently my air is filled with 4% of water vapor, simply because air contracted. Now, what happens when temperature rises? So I'm looking at this phase now, from this dotted line to this dotted line. When temperature increase, my relative humidity should decrease, and the logic is just quite the reverse. When temperature increases, from this small box, when temperature increases, air expands to become this big box here. The amount of water vapor does not change. It has not changed. Therefore, since my box has increased, air has expanded, I can now hold more water vapor. Previously, the maximum I can hold is 100 grams per meter cube. Now, the maximum I can hold is 200 grams per meter cube. As a result, previously at 10 degrees Celsius, when my relative humidity was 4%, my air was filled with 4% of air. However, as air expanded, the current 4 grams will seem to now take a smaller percentage of the air. The air currently at 20 degrees will only be 2% filled with water vapor. Now, what these two scenarios illustrates to you is basically the concept of temperature. What it shows you is that when temperature changes, contraction happens, expansion happens. That causes a change in the maximum amount of water vapor air can hold, and therefore changes the relative humidity. Okay, so you can see overall the relationship is such that when air temperature goes up, my RH decrease. When temperature went down, my RH increase. You can see it's in opposite direction. And when we have such an opposite direction, mathematically we call the two related in a inverse relationship. Okay, so what I've just written here is basically the relationship. This is the relationship between temperature and RH, and the keyword is inversely related. Okay, so what I've just illustrated to you basically is explain how temperature is related to a relative humidity. The answer is they are inversely related. Okay, now we are now going to apply this relationship, okay, to rainfall. Now, if we remember this illustration over here, okay, air can hold water vapor. Okay, it can be 2%, it can be 4%, it can be 5%, it can be 6%, it can be 7%, 40%, 50, 70, 80, 90. Now, there will come a point in time, a possibility that every single bit of the air is filled with water vapor. Instead of 2%, it can be fully filled with water vapor, and we call this 100% relative humidity. That means saturated, fully saturated. My air is saturated with water vapor. Okay? Air is saturated with water vapor. Okay, the keyword here is saturated 100%. What if now air is full of water, but yet, okay, there is one water vapor molecule. Okay, there's one Okay, ignore this. Okay, air is saturated. Now, based on the previous understanding, when temperature decrease, air should contract. Let's say now it is at 100% at, say, maybe 16 degrees Celsius. If it is to be reduced, let's say 15 degrees Celsius, basically I should see some contraction because my temperature has decreased. Previously mine is already 100%, no? That means now with a smaller volume, I can no longer hold that much water vapor. I cannot hold as much water vapor. Now, what happens is that some of this water vapor will no longer be able to be held in air. And basically, what they turn out to be is they no longer remain in gaseous form. They exit the air, and basically, what you form here as red dots here is no longer gaseous water vapor. It is actually liquid water vapor. That means these few molecules of water vapor previously held in air can no longer remain as gas. It has to exit the air and become liquid. So over here it is gas form, over here it is liquid form. And from primary school science, you already know, from gas to liquid, the process is called condensation. Okay, so therefore you realize that actually it's quite important to know this temperature here, because if I know this temperature, I know when my air will be 100% saturated with air. When I know when my air will be 100% saturated with air, I know from this point on when I decrease my temperature, water vapor molecules will start to turn from gaseous form into liquid form, and condensation will take place. This magic temperature over which 100% is achieved, and from then on causes condensation, is called dew point temperature. Now, I'm going to put this in the situation of rainfall. Okay, of the rainfall. Now you know, basically, water vapor in the end will condense into clouds. Water vapor, as it rises, it will form clouds. How come? Basically, the process is that as it rises, it experiences cooling. It cools. The water vapor loses energy as it rises and it cools. Basically, what it means here is temperature drops. And remember, when temperature drops, there is contraction. There's contraction of air. And because there's contraction of air, my RH increases, approaches 100%. That means maybe at ground temperature 25 degrees Celsius, my RH is 16%. Sorry, let's say 76%. And as it cools to 15 degrees Celsius, my RH will increase to 80%. As it cools to 10 degrees Celsius, maybe it reaches 100%. As it rises and it cools, my RH actually starts to increase. Now you realize that at this temperature, it's already 100. As it continues to go up, you can only expect when temperature is 9 degrees Celsius, it will be 100% still, but the air will start to condense. The water vapor will start to condense into liquid. Okay, and this condensation is basically what forms the clouds. So actually the real science behind the condensation and the cooling is basically RH. When when water vapor rises, it cools. As it cools, RH increase, reaches a maximum of 100, can no longer hold the water vapor in gaseous form. It has to be condensed into a liquid and therefore forming your clouds. Okay, so this temperature, as we have mentioned just now, the magic temperature at which it reaches 100% is what we call dew point temperature. Okay, dew point temperature. Now in the next video, when we talk about rainfall, you will start to realize, hey, what do I really mean in it? Okay, but whatever it is, let's come back to the learning objectives. What I've just done is I used the relationship between temperature and rainfall to explain condensation and rainfall. I repeat, I just applied the concept of temperature and RH to help you see how come condensation happens, how come clouds are formed. Okay, so this is what you need to know about relative humidity.